Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about specific gravity. This is a continuation of our discussion of fluids and fluid statics. You will recall a few things that we've discussed from previous videos. So recall that density for our purposes here is mass per unit volume. This means that the density equation can be written as rho is m over v. Now all solid and liquid substances have some sort of a density, and even gases have density associated with them. Solid and liquid we mostly treat as having a constant density for a given material. And again, that can be changed if the material is compressible, but that's neither here nor there for today's video's purposes. Second, we have the Archimedes Principle, and with the Archimedes Principle essentially helps determine buoyant force. You could say it governs buoyant force, and then that is by noting that the buoyant force is equal to the weight of fluid which has been displaced. I think those would be the two most important things to recall for today's video. Now, the new topic that we're introducing is what's called specific gravity. So specific gravity, often we use a capital S. It's defined as the density of a substance divided by the density of water. And so this would be specific gravity for a substance. Sometimes we simply represent this as something like S equals rho over rho naught or rho W or something like that. All right, so how do you determine the specific gravity for an object? Well, one way is that you just measure its density. So maybe you measure the object's mass, you measure its volume, and you divide it by the density of water. So density of water is approximately 1.00 gram per milliliter. This also means, for what it's worth, that by definition the specific gravity, of water is 1. Now there's another way of going about getting the specific gravity for an object. By the way, we're mostly again focusing on specific gravity, density, that kind of thing for solids and maybe occasionally liquids here. You can apply Archimedes' principle that the buoyant force is equal to the weight of the fluid displaced, and also that the volume submerged equals the volume of the fluid displaced. You can apply this principle to specific gravity. And what that lets you do is it lets you measure the specific gravity of an object by measuring the object's weight while not immersed in water, and then remeasuring it while it is immersed in water. All right, so the idea behind this experiment, this thought experiment, is this. Let's say that I happen to have a scale. So maybe I have like a scale like this with a little hook on it, and then I take an object and I weigh it in the air. Okay, so we could call this W naught. Maybe I weigh it in vacuum. So this is weight in vacuum according to scale. And then I take the same object and I dunk it into water. Okay, so now again I have the same scale. Maybe I put a string or something like that onto the object. I put this object into a container, and the container has in it water. Okay, well, this will now give me a new weight. This new weight is actually going to be, we could call this like weight when it's underwater, or weight submerged, or something like that. Let's call this weight sub. And so as it turns out, this will be less than the weight when it was in vacuum. Now, why is that? Because over here I have a force weight in vacuum, which is m times g, acting downward, and that's all that the scale can detect. That means the scale has to pull upwards with force of scale, and that gives me my weight. Well, when the thing is in the water like this, I have a downward force of mg, but I also now have an upward force F buoyant. And so the further force upward from the scale, W, force of scale, which is the same as the weight that we're measuring with the scale, will be mg less Fb. In other words, the measured weight while the object is submerged is equal to mg minus the buoyant force, whereas here it's just simply equal to mg. Now you can put these things together and note that if I were to solve for the specific gravity, I would have the weight of the object when it's in air divided by the difference between the weight of the object when it's in air and the weight of the object while it is submerged. This comes, of course, from the fact that this difference right here would be mg minus this quantity, which would just be the buoyant force. So, put differently, I've just done W naught over FB. Now, why does this work for a definition, not a definition, but why does this work for finding the specific gravity? Well, because if we look at this object, we have the weight while in air, which was mg, which is the density of the object. So we'll say density object times volume of the object times g. F buoyant, according to Archimedes' principle, must be weight of fluid displaced, which would be density of water times the volume of the displaced water, which must equal the volume of the object times g. S, on the other hand, is defined as density of the object divided by density of the water. But we could easily rewrite this equation to say, let's multiply both top and bottom by volume times free fall acceleration. So we could say object times volume free fall acceleration, and now we have water times volume free fall acceleration. But that's just the weight of the object in the air divided by the buoyant force. And that is in return the weight of the object while it's suspended in air or vacuum or whatever, divided by the difference between the weight in the air or vacuum or whatever and the weight while it is submerged in the fluid. You can also, for what it's worth, then use this to get the specific gravity of various fluids, because now you can measure the specific gravity of, say, a block of aluminum solid and now immerse it in oil. You'll get a different difference here, which means you have a different buoyant force, which means that you have a different density for that fluid. So in this case, weight when not immersed, we could say W0, which is m times g. We could have W random other fluid, that would be mg minus buoyant force for the fluid, and we would have weight while in water, which is mg minus Fb water. All right, well, if we look at these different quantities here, we have the object's weight already. So it's like we know what this quantity right here must be. And therefore, if we subtract W naught, subtract the weight in the fluid, we'll be left with the buoyant force in the fluid. If we do W naught minus W water, then we have the buoyant force of the object in the water. But that's just the volume of the object times G times the density of the fluid versus the volume of the object times G times the density of water. So if we divide these two things by each other, then you're going to end up getting the specific gravity of the fluid. S fluid becomes W naught minus weight while in fluid divided by W naught minus weight in water, which is just the fluid density divided by the water density. So that's how you determine the specific gravity of a random fluid, just by weighing an object 3 times in this case. Once in the air or in vacuum, once while totally submerged in water, once while totally submerged in the other fluid. All right, let's have a quick example before we finish today. So we have an object which is weighed in vacuum, it's weighed while totally immersed in water, and it's weighed while immersed totally in some oil. And we want to know what the specific gravity of the object is, and also the specific gravity of the oil. So for the object, specific gravity of the object should be the weight of the object when it is in the vacuum divided by the difference in weight when it is in vacuum versus in water. So this right here would be weight in vacuum. This one right here we can label as weight in water. And this one right here is the weight in the oil, which I'm going to use an L for since I'm already using an O or a 0 for weight in the vacuum. So this is 20 newtons divided by 20 newtons minus 16 newtons, which is 20 divided by 4, which is 5. So this thing has a specific gravity of 5. It's neat that we can do this because this means we basically just measured the density of the object without ever directly measuring its volume. In fact, we could now maybe figure out what the volume of the object is from this. All right, what about the specific gravity for the oil? So for that one, we're basically using this difference of weight in the fluid versus weight immersed in water. So you're looking at W0 minus WL divided by W0 minus WW. So that's 20 newtons minus 17 newtons divided by 20 newtons minus 16 newtons. And that is 3/4 or 0.75. So the specific gravity of this oil is 0.75. That means that it has a lower density than the water, and that means that if you poured it into water, it would eventually all float to the top. Well, that's all for today's video. I hope that you learned something from it, and as always, thanks for watching.